desktop and web, and servers. And it's MediaPipe is not like hermetically cross-platform. Instead, the components, if you produce components that fit into the MediaPipe framework, those components can be very portable if they're written in C++. It's also possible to write components that are tied to a particular platform, and so the MediaPipe is cross. The framework is cross-platform, but every component is not completely cross-platform. So here's some examples of where MediaPipe has been used in applications which are available to public. It's been used in some advertisements, such as this lipstick try-on advertisement. So what's happening in the first example here is that this is an interactive advertisement where a person can see their own face and can choose different colors of in this case, lipstick. And the way that it works is that it's doing face detection and face landmark mapping onto the video stream, and then it's using the landmarks, in this case the landmarks around the lips, to make a color change in the video frames. Another example was an advertising campaign for Stranger Things. This one used segmentation to cut out basically the image of the viewer who's interactively watching the advertisement, and to superimpose them on a background, which is the Stranger Things background. And another nice one is the lens living surfaces, right? And this is an application where it runs through Google Lens, through the camera, and if you happen to be looking at a magazine page through the camera viewfinder, and the lens can recognize a page that it has moving content, right? It has video content for that page, and so through the viewfinder you'll see the advertisement or whatever. I'm not sure it has to be an advertisement. The advertisement or the article will show up with moving running video when you watch it through the camera lens. So those are some examples of MediaPipe technology used in public. Inside of Google's products, MediaPipe has been used in several products. The earliest consumer for MediaPipe was YouTube. In YouTube, MediaPipe is used to view all the videos that are uploaded, to determine some characteristics of those videos. For example, one of the things which MediaPipe technology is used for is to choose a frame, a representative frame, to be used as the thumbnail for a video. So you can imagine that it's probably better to choose a representative frame, right, than choosing the first or choosing the middle frame of a video. It's also used to identify copyright violations. It's also used to identify objectionable content. So there are calculators that are being run through the MediaPipe framework that are used to answer these questions for YouTube. As I mentioned, Lens and AR ads, right, are consumers of MediaPipe. I mentioned hardware, the Nest cameras and the Nest home product. And then in addition, there are some of the Google Cloud services are powered by MediaPipe. So they're actually, these cloud services have a MediaPipe configuration and a MediaPipe inference pipeline, which is running inside the cloud service and powering the cloud service. So the most of this presentation is walking through an example of building an inference pipeline, a perception pipeline, for a particular task. So the task is this task, right? task of identifying landmarks on a video, which can include human hands in it. So the landmarks are like the knuckles and fingertips and palm. And so that's the objective. And so solving this problem starts with training a neural network to actually identify landmarks in images. So we assemble a data set of hand images, and we will manually label, we'll manually identify in those images the two-dimensional coordinates of the hand landmarks, right? So that's our training set, right? We have our training input and training output. Train a neural network to do this, using TensorFlow and deep learning, and we come up with a model which works pretty well over the test set, right? And the test set includes hands which are centered and take up most of the frame, right? So they're prominent pictures of hands. And actually, I think this data set was derived from video, right? So we started with the video. I remember my colleague Fan collecting this data, right? So he asked us to position our hands into a series of gestures, and then he used that series of images as the image test data for his network. And so this model was trained. It works pretty well. The difficulty is that when if we make the simplest, if we deploy this neural network in the most straightforward way, right? We just take the video images, each image, and we feed it into the neural network, and the neural network is usually able to find the hand landmarks, even though the hand is taking up only a small part of the video frame. So in a typical interactive video, right, the hand is a small fraction of the video frame. So this neural network, which was trained to recognize landmarks on hands which were kind of zoomed into the video, works fairly well for video frames where the hand is only a small part of the frame, but it doesn't work as well as it could. For one thing, it's expensive because the full video frame is a pretty large data set, and so the neural network consumes a lot of resources as it identifies hands throughout the full video frame, and then the accuracy is not as good because there's a lot of other data being mixed in with the image of the hand. So this shows how this simple perception pipeline would be implemented using these modules, which we call calculators. So there's a module to transform the image that maybe reduces the resolution of the image, maybe changes the color map for the image. We have to convert the image into a tensor, into just a vector of floating point numbers as input to the neural network. And then we run the neural network. That's another MediaPipe calculator. And then we need to convert the tensors into a data structure which can be rendered. And then finally, probably we're going to take that data structure and use it to render some marker on each of the images, right? So that we have a visualization of the result that we got from their neural network. So when we implement a pipeline like this in MediaPipe, all of the modules that I just mentioned are included in a MediaPipe inference pipeline, and so there's a single configuration which chains together these components. As I mentioned, the components themselves, we refer to them as calculators. The public interface to a calculator is a set of inputs of sequential data streams, and typically video or possibly audio input streams. And those streams carry a series of packets. Each packet, in the case of video, it contains one frame of the video. So the public interface to a calculator is a set of sequential data input streams and a set of named sequential data output streams. So in this case, these calculators typically have a single input stream with a name, for example, image, and a single output stream with a name, for example, tensor. Right? And the calculators, the API for defining calculators in MediaPipe includes a life cycle, which is basically a call to open, which initializes a calculator for a series of data, usually for one complete video. Repeated calls to process, one call to process for each packet of data, which arrives on all the input streams, and a call to close to allow the calculator to clean up after itself and to report a summary of everything it's seen. So I think in this simple inference pipeline, all the calculators are built-in calculators. So these are calculators that are part of the MediaPipe framework, and they include things like feature extraction and image transformations, and the TensorFlow inference call itself has a calculator in the MediaPipe framework. So one basic characteristic of the way that MediaPipe executes the calculators is that the data is collated according to timestamp. So every packet is labeled with a timestamp. In the case of a video, the timestamps are typically the presentation timestamps of the video frames. So we take the timestamps of each packet to indicate the time at which that data was recorded in the world, right? It's a time of an event that happened in the world. So collating all the packets according to timestamp is a way of bringing together the data that happened coincidentally in time. And that's usually the most useful way to combine the data inside of a media processing pipeline. If there's a need to use some data which is a little bit older historically, the calculators can have memory, right? So a particular calculator can maintain a buffer of recent packets. If it needs to refer to some characteristics of recent data, it can do that using the calculator's memory. Each of the calculators is a C++ class, right? And it has instance variables. The instance variables act as the memory for the calculator. So in this very simple inference pipeline, there are only 5 or 6 calculators, and so the pipeline, it remains fairly readable in either a textual form or in this kind of graphical form. But for more elaborate calculators, we can actually see some later in this presentation. For more elaborate graphs, it becomes harder to keep track of all the calculators and all the streams connecting them. And so we have a technique called subgraph, where we can designate a connected set of calculators as a single module, right? And one of these, and we call the module a subgraph. A subgraph as a component has the same public interface that a calculator has, right? A calculator has a set of named input streams and a set of named output streams. Subgraph has the same public interface, right? It also has a set of named input streams and a set of named output streams. And so we can, once we've essentially collapsed a given network of calculators into one subgraph module, then we can use it as if it were a calculator, right? And that makes the enclosing inference pipeline easier to read. So in this case, once we've collapsed the hand landmark, the very simple hand landmark subgraph into a single node, we have just basically two components, right? The hand landmark component, which runs the neural network, and the renderer component, which displays the results. And this component is actually a single calculator, single C++ class. That component is a set of C++ classes packaged together as a graph. And so this is a very, very nice, clean and clear inference pipeline. The problem with it is that, as I was mentioning before, it's the efficiency is not that great because we're using our raw neural network to process each whole frame. It's expensive and it's less accurate than it could be. So a technique to improve things is to identify a region of interest. If we can feed the landmark calculator with a smaller image, right, which includes only the hand, right, and not the whole video frame, then this neural network can operate quicker and it can provide a better answer, right, a more accurate set of landmarks. And so one way to approach this is to train another model, right, to train a second model. And this model we call palm detection model. And the purpose of this model is just to provide a bounding box, right? We give it a, we trained it with data with a lot of images like the ones you see here, and we've asked it to provide a bounding box around the palm of the hand, right? And it's able to do that pretty well. And it's able to do that even when the hand is closed or when the fingers are obscured. And then we use that bounding box as the region of interest for the landmarks, for the landmarks model. Landmarks model can run much faster and more accurately. And the way we make that region of interest is we just take the bounding box that we get from palm detection, and we use that to truncate the image, right? So we're giving a truncated image to the hand landmarks calculator. And so this improves the performance, right? With running landmarks directly on the video, we get a very low frame rate, right? Maybe only 1 or 2 frames per second. When we limit the region of interest to just the area of the hand, this can run much faster, several frames per second. The limiting factor now is the palm detection. The palm detection model is relatively slow because it still takes a full-size image as its input. So another approach that also helps is to use the landmarks from the previous video frame as the region of interest for the next video frame, because typically the hand is in roughly the same position between video frames. So if we just take the landmarks that were identified, we draw a bounding box around those landmarks, we use that as the region of interest for the next video frame, then we get the landmark model running at essentially full speed, right? Because it's running on a smaller region of interest, and we don't pay the price of running the palm detection model. So this works actually really well. The drawback is on the first few frames of video, when we don't know the region of interest yet, right? We wind up running the landmarks model over the whole image. And so the first few frames are relatively slow and inaccurate. And this happens again whenever the hand becomes obscured and comes back into view. So this is an improvement, but still not the best we can do. I think this model is the best. This inference pipeline is the best we can do, and it combines the palm detection component with the hand landmarks component, and also with the use of the previous landmarks as the region of interest. And so what this MediaPipe graph does is as long as the landmarks found on the previous frame are good enough, then we use those as the region of interest for the next frame. If the landmarks are not good enough for some reason, and we can kind of the network that does hand landmarks gives us an indication of how confident it was, right? So if it comes back with a low confidence, then we don't use the landmarks bounding box. Instead, we activate the palm detection, right? So palm detection runs when we don't have landmarks from the previous frame, and that gives us a reliable way to get a new region of interest, and to start running the landmark calculator again with a good region of interest. And as long as the landmark model succeeds, then we never have to run palm detection again, right? Because we're always able to use the landmarks from the previous frame as the region of interest for the next frame. So this is our best design so far for hand tracking, right, and hand landmarks. And right, it runs palm detection only as needed, and so it runs the landmark model in its fastest form. So we showed the hand landmarks model at a conference, and one of the things that everyone asked for was, can it recognize both my hands at once, right? So the way it was designed, as you could see, was that it was only handling one region of interest and one hand at a time. So we took the task of trying to enable this graph for multiple hands, and it still uses the same basic technique of using the landmarks as the region of interest for landmark detection on the successive frame, but now there are multiple regions of interest to communicate from the previous frame to the next frame. So that's one complication of this graph. We're able to do it in MediaPipe. And then another complication of this graph is that the question of whether we need to run palm detection again is not as simple as it was with the single hand graph. With this graph, it's possible that we go from seeing two hands to seeing one hand, and then maybe a hand appears again, right? So the only way to be aware of that is to run palm detection again, right? So this graph actually runs palm detection periodically. So like every 10th frame or something, it runs palm detection again. And that's what's used to capture the fact that an additional hand has entered the frame. So we published this this model, the hand tracking and hand landmarks model on Google's AI blog. And this attracted a lot of attention and a lot of curiosity. I think that there were several, well, there was at least one journalist who raised the question of whether this kind of technology could be used for sign language, for sign language communication, sign language transcription. And we're actually interested in that on my team at Google. There's some research going on, right, to see how much of that can be done. So most of the complications in this inference pipeline are there for the purpose of optimization, right? They're there to make the hand landmarks model run faster by running on a more focused region of interest. And performance optimization is one of the things that MediaPipe addresses. And there are basically two features in MediaPipe to improve performance. So one of them is GPU acceleration. The neural networks in neural networks through the TensorFlow neural network engine can run either on CPU or on GPU, and they typically run more efficiently on GPU. And so MediaPipe includes calculators for running the neural networks on GPU, and also a lot of the image processing operations can be run on GPU also. At the moment, this is done with a set of calculators which are specialized for GPU, for invoking their operations on GPU. And we're currently working on merging the calculators together so that each of our calculators can be configured to either dispatch its work to CPU or dispatch its work to GPU. And eventually that might even be done in a smart or adaptive way. Another performance optimization is executors. Each executor is basically a thread pool, which contains some processor resources, a set of cores, which may have some special characteristics. So we could create an executor that has maybe your fast processors or your high priority processors as threads in that executor thread pool. And then MediaPipe allows you to associate the special processor cores with special calculators, so that those calculators that have a need for extra or certain kind of processing power can be assigned those processors. Okay, and so some of the main objectives for MediaPipe, right, are to allow people to experiment and explore machine learning algorithms, and to make use of existing work, right, rather than having to reinvent everything. So given the hand tracking inference pipeline that we've designed, the next question is how can it be reused, right? How can it be used in different ways? And one way to reuse it is to replace a component, right? So suppose that we replace the hand detection and hand landmarks calculators with a face detection and face landmarks calculators. And that way, the same calculator graph, the same MediaPipe inference pipeline can function, but on a different job, right? And so it's going to produce the same regions of interest, and it's going to produce landmarks, but in this case, it'll be face landmarks rather than hand landmarks. So this is one way to reuse an existing solution to prototype or to try out an alternative solution. So another way to reuse the hand landmarks inference pipeline is to use it as the input to another pipeline. So in this case, suppose we take the landmarks, which were the output of the hand landmarks pipeline, and we use them as input to a neural network, which is going to recognize gestures, right? So it's going to take these I guess this is like 22 two-dimensional coordinates, right? That's what the hand landmarks are, and then and we're going to train that neural network to produce as its output a gesture tag, right? So in this case, this gesture gets tagged as yes or as yeah, and this gesture gets tagged as Spider-Man, right? Because it looks like the Spider-Man gesture. And then another way to make use of the hand landmarks inference pipeline is for effects, for video effects. So in this case, we can map a video effect to the hand, right, using the identified hand landmarks as alignment points for a video effect. So you see, we can attach a video effect to the tips of the fingers landmarks or to the palm landmark. Okay, so that's the. I hope I walked through an example of an inference pipeline, designed, iteratively designed, and implemented and deployed, using MediaPipe framework. So I'll describe some of the characteristics of MediaPipe framework now. The framework itself is in C++, portable cross-platform C++. The framework it publishes basically 3 APIs, right? Graph Execution API, which this is kind of the minimal use you could make of MediaPipe, allows you to load an inference pipeline from its configuration, run the pipeline with video data input, and extract from the pipeline the detections, right, that are produced by the inference pipeline. Or if the pipeline actually does some rendering, right, the output of the pipeline would be video frames. The next level of interaction you can have with MediaPipe would be the graph construction API, right? And that means that you are specifying a graph or maybe modifying an existing graph. And that API is the most popular version of that API is a protobuffer textual description. I mean, protobuffer is actually a binary format, right, for writing configurations, but it has a textual representation too. So we typically define an inference pipeline in MediaPipe as a protobuf, which is protobuf is something like a JSON configuration file. And then the most you could interact with MediaPipe would be to actually produce new calculators, right? Which could be fit into existing or fit into new inference pipelines. So that in that case, you could someone could, for example, create a MediaPipe calculator that invokes a PyTorch inference, right, on a PyTorch machine learning model, or there could be additional MediaPipe calculators for various simple machine vision operations, such as edge detection, for example. And so the blue boxes are all included in the MediaPipe distribution. MediaPipe makes use of TensorFlow, OpenCV, and OpenGL and Eigen. So those are some of MediaPipe's dependencies. I mean, in addition to the cross-platform C++, there's a limited set of utilities which are platform specific, like utilities for Android and iOS, to help with deploying and to help with debugging MediaPipe on those platforms. Yeah, and then right, and that's the platform. So where you can find MediaPipe, you can find MediaPipe on GitHub if you go to the URL mediapipe.dev, that will take you to the MediaPipe GitHub, and there you'll find all the examples, including the hand tracking example. There are a couple of other servers that you can find. Docs.MediaPipe has the documentation that accompanies the source code, and that's pretty straightforward. Viz.MediaPipe.dev is a server service hosted on Google App Engine, which is helpful. It's kind of like an IDE for helping to organize inference pipelines in MediaPipe. If you have your description of your inference pipeline, including the calculator names, the input stream and output stream names. If you have defined an inference pipeline, you can paste it into this web page, and the web page will show you a graph view of the pipeline. And that we found around at Google that we almost always refer to this view of each pipeline. It's much easier for us to understand the flow of data through the pipeline when we see it this way than when we see it in a textual view. And this service does a couple of other things too. It can be used to profile a pipeline. So if you have a pipeline which is doing something like hand recognition, it's processing maybe 10 frames per second. You can record a profile, trace of all the events that happen while it's running on a device, and then you can copy that file to this web page, and the web page can show a timeline. It can render a timeline of the series of events that happened while your inference pipeline was running its inference. And it's a nice nice graphical view of a series of events, and it actually connects back and forth between the events in time and where the events happened in the graph, in the graph, the visual view of the graph. This application does one other thing too. For some of the some graphs that are limited to a certain set of calculators, there's a run button, and you can actually push run on the web page, and it takes the inference pipeline and its calculators and converts them from C++ into WebAssembly JavaScript and runs it right in the browser. So you can actually see the inference happening, bounding boxes, being placed around faces and hands and so forth, running in the browser, and it runs surprisingly fast. It's actually WebAssembly is a fairly efficient way to run these inference pipelines. So at the GitHub repository, you can find these examples. All these examples. There are about 6 or 8 examples, and there are versions of them that run on Android and on desktop and on web. So to follow progress on MediaPipe, we will post updates about MediaPipe's progress on Google Developer Blog, and occasionally MediaPipe may be mentioned on Google AI Blog, as it was for the hand tracking demo. And then if you go to MediaPipe.dev on GitHub, you'll see the releases, a series of source code releases in the MediaPipe code base. So that's the end of the slide presentation. I can show you a couple of demos here. So here I'll build the hand tracking application. So what I've done is I've cloned the GitHub repository to this workstation, and then I've built the one of the targets in the MediaPipe code base using it uses the Bazel compiler to compile the C++ code, and then I'll run it. I want to run hand tracking. Yeah, I think this is the one. Yes. So here's the hand tracking running. So I can put my hand there, and you can see that it's reading these video frames through the webcam on the workstation, and yeah, and it's able to. I guess this is maybe 5 frames per second, maybe 10 frames per second. So the performance is not super great, but it's pretty good. And this is the single hand model, right? So it won't be able to recognize two hands at one time. It can only recognize one hand at a time. Okay, and I'll show you one more demo before I go. This is a technology called AutoFlip, and so I will compile the AutoFlip. Let's see here it is. Yeah. So this is one of the demos. I think this may not be on the GitHub repository yet, but it should be there soon. And so it can be compiled as well. And then, so what the AutoFlip does is it's an automatic framing technology, right? So it finds the area of interest in a video, and then reframes the view, a window into the video to cover the area, the interesting occurrences in the video. And so this is useful. You can imagine this could be useful in a teleconference, right? When one person's speaking, you'd like the view to focus on that person, and that's how this technology was developed. It found a very interesting application at Google. Google has a large number of advertisements. So Google is mainly an advertising company, right? So the large number of advertisements that are formatted for landscape displays, like web browsers. But nowadays, most of the advertising actually is consumed on cell phones, right? And so they're portrait mode, and so all those advertising video content wasn't easy to display in portrait mode, right? It would typically get scaled down so it was barely visible. And so what AutoFlip was able to do is to take the video at full size and then to reframe so that it finds the useful part of the video in the cell phone, and it makes those existing advertisements, deployable on cell phones. So I will. So let me show you the. So here's the video in landscape of snowboarding, and so the goal is to produce a video which has an aspect ratio of just a square, 1:1, but still captures the interesting part of the snowboarding video. So this one will run in batch mode rather than running interactively. So let me find here. I think this is it. So now this is the AutoFlip perception pipeline running in batch mode, and so it's running on all the frames of the skiing video. Yeah, and it takes a few seconds to get through all the frames. I'll wait for it to finish. Okay, there's done. And then we can find that this is the output video. So this has been now reframed at an aspect ratio. It's attempting to keep the interesting elements of the video in the small area of the rescaled video. So that's the AutoFlip. This is another output from Google Research, right? Where Google Research is developing technologies like this for products like the home device, but they'd like to also publicize their work, right, and make it available open source, and they do that through MediaPipe. Okay, so I can pause for questions if there are any questions. Okay.
I don't have a good idea of what's going on behind the scenes. For example, with the hand tracking example. So it sounds like you have N detector, palm detectors, and hand landmark tracking models. In the example with 3 hands simultaneous. First of all, why not just use one detector? Because one detector should handle, find all the instances of the palms. And then landmarks being separate, and also how does the like if it's on the GPU or the GPU delegate or something, how does the GPU handle in resident multiple models, and what's the limit of that?
Sure. So I'll try to answer both of the questions, right? So I think there are probably some other ways to organize the hand tracking, right? And certainly we could train a multi-palm detection model, right? That would actually detect all the palms in a single pass, right, with a single neural network. But I think that the way that this solution evolved, right, was to sort of start with the simplest thing first, right? A single hand landmark detector, right, and then a single hand palm detector, and to show that working, right? And once we'd shown that working, it seemed like the easiest way to proceed, right? The easiest way to get more efficient, landmarks to work, and the easiest way to get multiple hands to work was to take the models that were already working, right, and to chain them together. And that's actually kind of a design pattern, right, around MediaPipe, is the idea of, rather than, and this is a little different than the design pattern around TensorFlow, right? The TensorFlow team would probably tell you, right, that there's an elegant way, right, to get a single model, right, to do all this work, right, and to do it efficiently with deep learning, right? And they're right about that, right? But what MediaPipe is enabling is an alternative way of engineering things, right, where you get the simplest piece to work, which is necessary, and then you chain it together with the other components, right, to make it do a bigger job. And could you say again the second question?
And how is the GPU handling all these instances of TF-Lite models?
Yeah. So I think that the way that GPU is addressed inside of Drishti is that there's an API where you can build a calculator whose tasks run on GPU. And so the code is actually C++, right? And it dispatches a GPU task for each call to process. And those calls to process, they get dispatched to the GPU queue sort of independently, right? I mean, the calculators in Drishti in MediaPipe will run in parallel. And so when they're backed by GPU, they'll dispatch tasks to the GPU queue in parallel. And then the GPU, depending on how many resources it has, right, it will maybe run those tasks in parallel. Maybe it'll have to sequentialize those tasks. I think that's what will happen to the GPU tasks.
Is there a limit to it? I mean, if you have 10 TF-Lite models, wouldn't the GPU sort of start becoming bogged down?
Yeah, it could, right? It would. What we'd see would be probably longer latency and the lagginess, right? I think that the GPU queue will queue up indefinitely, but it's true that the GPU task will be done, much later, right? And so what we'd see would be the output would lag the input by maybe a whole second. And we know then that we've kind of overloaded the resources for MediaPipe graph. And so there is a calculator that we offer that addresses this question, right? It's a flow control calculator. And what it does is it limits the number of executions, the number of frames that are in flight. And if we're receiving frames at a fixed rate, like 30 frames per second, we actually just drop some frames if there are too many frames in flight. And that's a way to manage the burden that the MediaPipe inference pipeline is placing on the hardware. Yes?
Could you use this technology in live streaming? Let's say streaming YouTube live, and the viewer show like this on the camera, like this.
Yeah. Maybe
you should get the emoji, like a comment or something like that.
Yeah, definitely, right. So the application of MediaPipe in lens, right, in the lens on the camera is typically presents that way, right? It's not used for public live streaming, right, but it's used through the viewfinder. And I think no one has done this yet. I think maybe Snapchat has a bunch of filters, right, do something similar to this. But this MediaPipe technology definitely, it's running interactively. It's running live on live video at a frame rate which is good enough, right, to work interactively. And so it's definitely applicable for use cases like that.
Or maybe for conference or something.
Yeah. And in fact, the technology behind the AutoFlip, that was originally built for actually recording conferences like this, right?
Oh.
It was actually called I forgot the code name. It was named after a movie producer, and it was it works operates like Facebook's portal works now, right? In that it would have a camera that has a wide view, and it would truncate the image to the area where this active speaker is.
I think the live sign language would be a good example of when a person doesn't know the language and
Yes.
other could translate. You
Yes.
can integrate this live.
Yeah, and that application really captures people's imagination, and we were even working on it, inside Google. But it turns out to be a very, very difficult problem because sign language, we didn't know all this, right? But sign language is a very subtle language, right? It has a lot of subtle gestures that are part of it, and the gestures are often truncated and combined together. So it's very hard to recognize it, with machine learning. Well, something I didn't realize initially was that sign language is not English, right? So there are two different languages, right? So you have a whole translation also from one language to another. Yes.
I was curious when you were mentioning about compiling to WebAssembly, where is the pipeline like compiling the Python interpreter and then feeding Python code into the, I guess, translated Python interpreter to output to actually have like the machine learning code run on WebAssembly?
So yeah, I think that what is happening, and it's a pretty elaborate chain, right? But all of the calculators in the MediaPipe pipeline, they're all written in C++, right? And so what the WebAssembly deployment does is it cross compiles that C++ to WebAssembly, right? And I think C++ is a typical source language for WebAssembly. And so if your pipeline has been defined using Python, that turns into a protobuffer definition of the pipeline, which just names the calculators, right? Then that turns into a set of C++ objects in memory which are communicating, right, to actually execute the pipeline. And then that in turn can be translated into WebAssembly JavaScript, right, to run in the browser. So that's what's happening, I think, is that we have a complete C++ process running as JavaScript in the browser. And the C++ process is the MediaPipe framework. Yes.
So this is probably dumb, but say if I have a new version of the Python detector model, I want to test it against existing one.
Mm-hmm.
Why duplicate the pipe and run it at the same time, or better to somehow like get the source and put on two nodes?
It's a good question, right? And I think that this is the problem of evaluation. And we have actually used the technique, the first technique you mentioned, right, of building a single MediaPipe inference pipeline that does both alternatives and renders both alternatives, right, simultaneously. And that's kind of useful as a side-by-side comparison. That's one way to get an intuitive, subjective understanding, right, of the quality of the two models. Typically what we do is we look at each one separately, right? Because that way you get the full power of the device running on each of the two models. But the problem there is that it's actually subjectively very difficult to know which one is really better. Teams that get more sophisticated with evaluation will typically maintain a corpus of video, right, which is the evaluation video, and then they will define, if they can, metrics, right, on the performance of the different models, as far as accuracy or compute efficiency, and then they can rerun the corpus against each of the new models. So that's the real sophisticated technique, but it takes a lot of infrastructure building, right, to get eval to work in that way. Yeah.
Even in a single detection model, if you want to run on a GPU, most of it can run on the GPU, but the last portion, the non-max suppression, usually runs on the CPU. So is MediaPipe automatically handling, okay, this portion runs on the GPU and this portion runs on the CPU, times n models, all that?
Yeah, good question. So I think that MediaPipe is, at the moment, is not nearly as sophisticated as that, right? Right now, each calculator is either dispatching only to CPU or only to GPU. The TensorFlow calculator is an unusually elaborate calculator, right? Because it invokes the whole TensorFlow inference engine, behind the calculator. And so I think we'll inherit all of the things that TensorFlow can do, right? So TensorFlow for a given for one evaluation of a model, right? TensorFlow, I think, is capable of doing its own parallelization and allocating resources between GPU and CPU. Typically, I think what happens in MediaPipe is we have all the GPU executions happen using something called TF Lite, TensorFlow Lite, and the TensorFlow the other TensorFlow calculator, I think uses only CPU in the usual configuration. So that's how we typically are building these inference pipelines, is that we are just picking and choosing. Let's use TensorFlow Lite here. Let's use TensorFlow here, and that's basically limiting us to GPU and to CPU. Yes.
Questions. And the first question that if you had went to work with like IBM not because you don't find like image models. Typically, a picture from your gallery, snap a picture, or
Yeah, we have had some clients inside Google, right, who are using MediaPipe to batch process a set of still images, right, rather than video. And in fact, a lot of the inference pipelines process the video images separately anyway, right? They don't actually have any memory in the calculators, and so each image is processed separately by the pipeline. And we have had some clients that define just a still image processing pipeline, right? And then they'll organize the images into a sequence, right? And the MediaPipe requires them to assign a timestamp to each image, but that's an arbitrary. They typically just use an increasing integer, right, in order to be an identifier for each image.
okay, so
It can be used that way, yeah, and it doesn't take advantage of some of MediaPipe's capabilities, but it definitely can be used to do still image processing.
right. And then another question, one thing, and I'll just ask one more. I tried playing with MediaPipe. It took an Android about 30 minutes. So how do you expect to make some small changes, like just to build it and play on my phone is fine, but if I want to actually take it.
Yeah, so I think that I think that the cost there, I think the biggest cost that we found in building MediaPipe from source is building TensorFlow. I think we have a dependency on TensorFlow, and so we wind up building TensorFlow from source when we build MediaPipe from source. And we were a little disappointed at how long that takes, right? How much of a cost that is. So there are a couple of answers. I think that that we have. Let's see. Well, I think so. We have a solution for being able to package MediaPipe as a pre-built library. I think that there are now we can package it as an AAR, right, an Android library, and I think we have also a desktop library, some kind of shared object target that we can build. So we have that, and that the main use case there is if you have an existing application, right, and you would like to integrate a MediaPipe pipeline into the application, you don't want to, for example, you may not want to use Bazel, right, as your build tool. And so this allows you to run Bazel only on MediaPipe, right, and then bring the compiled object file into your application, and that might be helpful in the cost of the start, the getting started cost. For example, we might be able to have a prepackaged, pre-built MediaPipe framework, or maybe we could consume the TensorFlow framework as a pre-built framework. Because I think most TensorFlow users do that, right? So most TensorFlow users only change Python code, right? And so the TensorFlow library remains pre-built, right? And they can even just consume the standard pre-built TensorFlow library. So yeah, I agree with you that that's a significant drawback building MediaPipe now. But we're aware of that it's a pain point, and so we'll look for some way to work around it. Yeah.
I'm trying to understand, since this is new for the public, and you see, like, all the things you mentioned, we could actually build models on PyTorch using Torch, tensors using TensorFlow, and at the same time, we can run the same things on Edge using OpenVINO tools from Intel. So, and Google has recently released AR Core also. So, which is also something that you can use filters and all these augmented reality stuff. So, how is it different? Like, I mean, is it like all those tools are built in just one single platform? Or
No, it's a legitimate question. I think there's a significant overlap, right, between those different toolkits. And so the history of MediaPipe, right, it has been used inside Google, right, as a way to package the Google's research, right, so that it can be incorporated in products. So the idea there is that MediaPipe is kind of acts as an interface. So once a product has accommodated MediaPipe in that it's adopted MediaPipe's dependencies, right? It has essentially a MediaPipe container in the product. Then various new pieces of research, right, can be deployed to the product through the MediaPipe container. So it doesn't provide probably any functionality which goes beyond what's provided by ARKit or provided by TensorFlow, but it's an interface layer specifically for inference pipelines, right? So it says that if you have in your app, in your product, if you have if your product does video processing, your product does real-time notices or something, you have a place where you could consume machine learning inference pipelines. MediaPipe it can act as the channel between like research teams who produce inference pipelines and product teams which would be consuming inference pipelines.
but there are other inference recipes also, right? Like I just mentioned, Intel has released OpenVINO toolkit. So what is it?
So I think that the distinction maybe is so MediaPipe aims to be able to integrate multiple trained models and to integrate those with other image processing components, and to do that in a repeatable cross-platform way, right? So it's defining an environment, right, which is reproducible and cross-platform, and encompasses all the steps that are involved in specifically in an inference pipeline, right, going from images to detections to other detections to other images.
And also the calculators that you mentioned, the pre-built selected calculators are only for the face recognition, face detection.
Well, not even for that, right?
And also includes object detection, space detection, and other segmentations, other.
Yes, and actually those appear as